Hi everyone, in this particular video I have tried to condense all the things that you need to know about databases and the most frequent questions that are asked generally around it in the interviews. I know that your internships and placements are right off the corner and then you are going to be sitting for these companies where you will be asked these questions. So make sure to go through this 30 minutes short crisp explanations of all these questions. Even if you don't know databases, you will still be able to retain some of this information and should be a good gist to go through first and then maybe read more about databases. I've also added the links that would be relevant to read more about databases if you want to do that on your own. So enjoy the video. It's just a 30-minute video, but you will learn everything that you need to know and maybe it's just gonna save you an interview altogether. See you in the video. Welcome to the series on Core CS most frequent questions, where we talk about the common interview questions that are asked on different Core CS subjects. And today we are talking about databases, right? Database management system. So we'll talk about the most frequent types of questions, what are generally asked and how to prepare for them. Now this can even serve like a short summary of the whole subject if you have read it before, so that you are ready for the interview. Now, I think in databases, there are like two different broad realms in which questions are generally divided, and these divisions create different kinds of questions and you need to be aware about both of them. One is designing and querying the databases, like how do you design a good database? There are things related to SQL on querying, right? These kind of things are generally asked in interviews. How do you normalize? How do you make sure that anomalies are not present and things like that? Then there are also questions around how does databases work, what are they, what kind of features they support, what is RDBMS, partitioning, sharding, bunch of things like this, right? So again, questions related to the systems mechanics of database management systems is also asked. So these are two broad realms and both of them needs to be prepared separately in my opinion. But again, we'll go through the questions that are listed here in some form or the other. I've tried to reorder them in a way that we can logically learn everything, and so that it also serves like a summary of the whole topic altogether, right? Let's get started. Let's see how this goes. So we'll start with the right hand side one, which is what are they, why they work and how they work and stuff like that, because I think that's more important. So general questions that you might get started with is what are databases, what is database management system, what is SQL, what are the difference between any of these two, database versus database management systems, right? These are things that are generally asked in as a starter questions of databases, right? And you are supposed to be knowing the clear differentiation between them, right? So database just means systematic collection of bunch of data here and there, right? It's just a systematic collection of the data. That's it. That's a database. Now, a management system built on top of this data to be to ensure that you can actually store these things efficiently and you can organize them, you can build indexes, you can query on top of them, is something called as the management systems that handles this database, right? We also have SQL as a language, which basically works as an intermediate, so that if you have a database, you want to ask questions or ask queries or update that database inside the database management system. So you use a language to communicate that to the database management system. The language used is SQL in most cases, right? But there are more languages, but SQL is the most common one. So on the internet, if you think about it, we have internet requests coming to the website's backend. There are web servers that handle it. Then there are some services that might be there, and it calls the database. So my understanding is this software that you see over here, the database that you see, is actually a database management system. Inside that, the databases of the corporation would exist. And on this wire, when you are from your server, when it asks the database on what exactly to be retrieved and what needs to be saved and things like that, the thing that goes on this wire can be an SQL, right? So that's what is essentially a database, is three core terms, right? Sometimes questions are asked around what are the different types of database. Now, most common one would be relational database, where you have these rows and columns and stuff like this, right? Which I think most of you would be familiar about. But you also have you have analytical databases, which is generally used for keeping large blobs of data and then analyzing them later on for insights and stuff. They are not very, either they are read heavy or write heavy, and mostly they are read heavy, you build analytics on top of it. So there are database systems that support that. You also have column family databases, graph databases, right? key value databases, right? Document databases, these kind of NoSQL databases are also supported, right? And there are plenty of examples of these things in industry also. Like there are different implementations of these types of databases, but just know the names because somebody might ask you that in an interview. One very, very common question, Vivek. I have seen that you can actually store a file in C++ and just store whatever is required. So why not just use files to store data and use a database? Because first of all, files are local and there are a bunch of differences between the them, right? This database management system makes a lot of things easier, which we don't really appreciate when we are actually using it. For an example, I have highlighted the main points with green, but sharing of data becomes easy because files are a local concept, right? Like it's a file residing on one computer. But databases might replicate or duplicate the files or keep it in a way that it is accessible around in different parts. Multiple different servers can access it, as well as it is like you can say format agnostic. So it's not necessarily a TXT file. It can be any file that you kind of save and everybody can access it, right? You don't have to like focus on encoding and stuff. Security is something that is super important. Like files, anybody can read and kind of tamper with it. But then in database, you can create security levels and you can give accesses to certain things to certain users and stuff like that. These things aren't possible on a single file. Recovery mechanism is super important because if files get deleted or the computer gets crashed on which the file is, there is no way to recover it. Like in this case, there is, if something fails, there is a try of recovery of the file. I mean, if it gets corrupted because of some malicious or some interrupted action that was happening, it gets recovered. So that kind of recovery mechanism is there in database management systems. Of course, if whatever system you have the database management system on gets on fire, then you might lose that too. But again, like it's much better than having just a file which gets corrupted, like partially written and half of that is not written and things like that happens, right? Then concurrency problems are super important, which means like a file when being read by a program, another program might not be able to read it. Or if you allow that to happen, if both of them are writing and reading together, you might have some problems in the data that is there in the file at the current time. But like DBMS kind of handles that really well. Then data redundancy and inconsistency. So file system like are created by different programmers, so they are so files are duplicated a lot, but then DBMS tries to make like data redundancy as minimal as possible so that you can join and then query on top of data, things like that. So this is also there. And obviously you can, file system is a very local approach, quick, cheap, but you don't really want to do that when you are building a production grade server because you don't want to lose data. But DBMS is the approach that we go towards with that. What is RDBMS? It's basically like you have records or tuples being stored in rows of a table kind of structure, and that is what is called relational databases. So there are a bunch of relations that are being existed in over here. That for employee ID 1, you have the name, post, and salary. These are the relations that you have with things, and there are different names like columns are there, which are the fields or attributes. There are something called as keys, primary keys, which means something that is unique and identifies everybody uniquely. You have number of columns called degree. Cardinality is the number of rows. You have domain is what is the range of values that are feasible in a particular column, things like this that exist in an RDBMS concept. But RDBMS just makes it a relational database management system. The ones that we traditionally use like SQL, MySQL servers and Postgres and all these things are RDBMS. Now there are tons of questions that are generally asked in interviews around how is things actually stored, what are indexes, what are table scans and like index scans, what are different, how is data actually stored, how are data actually manipulated in fact, right? So this is something that you need to be clear about. So from just as an example, you need to think about this. Let's say you have a particular like table where you have employee ID, employee name, employee date of birth, and employee salary. You would generally create a row ID. This is, I'm trying to take an example of Postgres, but it adds a row ID in front of it, right? And then it tries to create pages of the data that is there over here. So let's suppose a page can fit 3 rows. So what will happen is the database will try to store these things in pages of 3 rows. So 3 rows total. So row ID 1, the employee ID, name, date of birth, this, and then there is a separator, and then again the next row. So that will be in the page 0. Then page 1 will contain the row number 4, 5, 6. The page number 2 will contain roll number 6, 7, 8, 9, and so on. So this is how it will be stored, right? So like if you think about it, like there is a fixed size page that are being stored in the memory, and this can be in fact like small files itself, but they are being stored in the memory, and then these pages are what are being retrieved to be read and then showed the result on. Okay, so these are the pages that are built in the memory. We can try and like think of it as a database is nothing but a computer which basically is running the software piece that helps you get the query, take queries, handle it. There are a bunch of other processes that goes on inside it. I don't want to make it complicated, but inside it you can think of a hard disk which will save actually these pages and stuff, right? And the software that is running on the computer will read these pages on demand whenever it's required and stuff. And there are a bunch of optimizations built on top of it, but I don't think we need to get into there right now. One obvious optimization that you need to know about is building indexes, right? So it's like a separate structure that has pointers to, this is, let's suppose, the heap, okay? And this structure which stores these pages is called a heap. And the indexes is basically a separate structure that you built so that you can query efficiently. For an example, we know that I want to query things based on employee ID, right? And over here, it looks like it's sorted, but it might not be, okay? So I might insert a new row, which might be of a different employee ID, which might be lesser than what Shubham has, right? So what we might want to do is we want to create another smaller data structure called index, which will contain just the data on which we want to like build index on, like this 101, right? Which is the employee ID. And save a pointer that, hey, it is saved in the page number 0, row number 1. Page number 102 is present in page number 0, row number 2. 107 is stored in, so see, 107 is stored in page number 0, row number 3, right? So this is how you are saving. And obviously, since you are not saving the whole data, this data can store much more number of information in one single page, because it's just one number and some pointers, right? So it's much smaller, so more things would be available. Plus, this pages will be maintained in a sorted order, like unlike this one where everything was just by row IDs. This particular pages will have the row employee IDs in a sorted order. So what will essentially happen is, and how is that sorted order maintained? It's basically these pages are being maintained by something called as B tree. You can read more about it, but I don't want to get into that details, because generally, like, you just need to tell the name that it's stored as B trees and stuff. Nobody gets into too much of details of how does B tree as a data structure works, but it just makes things remain sorted, and insertions and removals are super fast, because you might want to remove a row or insert a row, right? So every time you basically have a page, and if you want to build an index on top of a particular column, there is a separate structure like this that is created, which contains the data on which you are building the index on, and the page number and the row number, the entry number in that particular page, right? So the rows that are there. So rows number 4, row number 5, row number 6 is there in this page number 1. Yeah, this should be page number 1, I feel. Yeah, so this is basically the idea. Now, when you get some certain query like this, like select star from employee where employee ID is equal to 1, 2, 3, 4, and you have not built the index, what will happen is you don't know whether employee ID is sorted or not, right? So you will basically go through all the pages, you will scan the first page, read and see that, hey, 1, 2, 3, 4 is not present in the employee IDs here. You will read the next page, see the employee IDs, you will go through all the pages. So you will eventually have to read all these pages from the disk, and that is very costly, because reading from disk is a costly IO. Okay. But what if you have an index, so which is index scan, is basically you go to the index first and say, hey, I want to look at 1, 2, 3, 4. Now, since this index is sorted by employee ID, you can think of it being a binary search, but in B tree, you can do a traversal and you can find out, hey, 1, 2, 3, 4 lies in the last page of the index. So last page says 1, 2, 3, 4 is present in page number 333, and as a row number, the row ID of that is 1000. So go to page 333, fetch that page and get the row number 1000, and you will directly have the data for the 1, 2, 3, 4. So this is essentially how quickly it can do it. Like you need to fetch this page, the index page needs to be fetched. So first one page and then just the second page, right? So it makes the fetches much more faster, much lesser number of disk IO. But then again, the cost is you have this extra structure to be maintained in memory. You have to update it and like as the data is changing over here. So those things are there. Like there is a trade-off between them. But again, this is how indexes make your query fast. Now, sometimes questions around database partitioning is asked, which means, hey, what is database partitioning? So essentially the concept is if a particular table or a particular database is getting very, very large, you want to, a particular table specifically, so you want to divide it, let's say, into 2 different tables or 3 different tables where you have different information based on your requirements. Say in a particular table, you have a username, profile ID, connections, and content authored. So you can split it into 2 different tables with the same IDs being linked, and then you have the username and profile data here, and then connections and content authored here. And maybe this table is something that gets read much often rather than this, because connections and content authored might be something that you hit only when you go to that user's page, but maybe like you want to show certain small chips and stuff about that user everywhere. So a lot of profile data might be fetched about that user. So this table you can try and optimize further, and this one you can keep in a separate place. So it just helps you scale things up very, very quickly. You can also divide it into like ranges and stuff and divide horizontally. So this is called horizontal partitioning. This is called vertical partitioning. In horizontal partitioning, you divide a particular table based on ranges of a certain column's value, right? So in this range, whatever the items are, this will be there, this will be there. And it might be relevant because some people query only like high priced things, some people query only low priced things and things like that. So you can create the queries around that. Then there is a concept of sharding. Basically, the concept is very similar to partitioning, but when you partition that and send it to different servers, right? Right now, we just divided the table, but those tables are in the same database management system. But if you make these database tables that you created just now, I'm using partitioning, move to different servers and try to manage that in a proper way, what you're essentially trying to do is basically database sharding, right? There are different databases, different servers, and each contains different partitions of the data. So you'll have to decide which part, if you get a query, which partition this query should go to and things like that. So that is called database sharding. And there are like advanced system design concept like consistent hashing and stuff, which you can read more about. But I think at a like core CS level, you don't need to know about these things. Differentiate between an exclusive and shared lock. This is another thing that is generally used when you like send a query to the database. What happens is if the query is updating a particular row, right, you need to make sure that nobody's reading that row at that point in time, because then you might have a problem, because the reading one might partially read the correct value and partially read the wrong value, right? So there are locks designed, which is called exclusive locks and shared locks. Exclusive locks basically is essentially a write lock, you can say. Basically, you will hold the row, right? And nobody else who is trying to update or read it will be able to access it anymore because somebody is updating it. But then shared lock is a little different. Shared lock is basically when you get a shared lock on a row, nobody will be able to write on it, but others can read on it, right? Because if I'm reading a book and you are reading the same book, it's perfectly fine, right? Because the book is not changing. But if I'm changing the book and you are reading it, that's a problem. So while somebody's writing, things shouldn't be shared. It has to be exclusive. But when somebody's reading, it has to be like, it can be shared more. So that is how it's managed. These are 2 different types of locks that you can get on rows, on certain set of rows, on the whole table, things like that. But essentially, this is what is there available when you are handling a transaction, right? Next, we come to like how to design databases and stuff. And there are like tons of things around this. Like there's something called as ER diagrams, which is basically trying to build a relation of the real world system that you want to actually keep in database. Like student relation, student attends course has subjects, teacher, lecturer teaches a subject has different properties or attributes, which is lecture ID, subject name, things like this, right? So you try to build a diagram like this, which is called ER diagram. You can read more about it. And then from this, you convert it to a schema on how the tables will be related, who will connect to whom and stuff like that, right? So over here, like course has a student, right? So you have a link between course and like a student can be enrolled in certain course IDs and stuff like that. So there has to be some relation between them. So you can build schema from that. It's not the perfect database schema, but it's just a schema on how the objects would be related, right? So you generally first build the ER diagram, then you build this, and from there you write the table structures and stuff. Then there are questions related to like types of keys in databases, primary key, candidate key, okay? Basically primary key is something that is unique and shouldn't be null. Candidate key is something that can be a primary key, but a table can only have one primary key. So everything that you can choose that uniquely identifies every row is a candidate key, but one of them can be the primary key. Then there is foreign key, like which helps you link one table to other, which is basically it identifies uniquely the row in some other table, is called a foreign key. Composite key is basically combination of two or more columns that makes it unique. So a candidate key, which is combination of multiple columns, right? So for an example, if you have a registration of a student in a course, then student ID comma course ID has to be unique in every row, right? Because a student can be enrolled in one course exactly once. So student ID comma course ID can be a composite key. Unique key is a constraint. Basically, it just makes sure that that particular column is unique. It's an enforcement. It's a constraint on top of that you can build. Super key is one or more columns that can be used as unique identifying a record. Like it's a little different from what you say as composite key, because in this case you can have redundant columns extra, but in composite key, like each of the columns cannot provide uniqueness alone. Okay, so you can have additional columns that are not necessary. Then there is secondary key, which is a secondary key is a field that is used for sorting and searching, essentially building indexes and stuff, right? And surrogate key is basically a key that is artificial identifier for an entity in a database, right? So basically, if you think about Postgres, what you do is like whatever the tables are, you have a row ID being introduced in front of all of them. So that row ID is a surrogate key that is uniquely identifier of everything. Even if you don't have a primary key, that can behave as a primary key. Like when you have students and data, we add a student ID, which automatically increments by 1. So we aren't trying to, the number doesn't make any sense, right? But we are trying to create a new number for everybody so that it's unique. That's called a surrogate key. By default, students doesn't have anything unique. Like two students can be perfectly the same thing. Their name, the parent's name also might be same, right? Okay. So this is essentially different keys in databases. Now you might be asked questions around anomalies in databases, like update anomaly. Like for an example, if you want to update, given this particular table, which is like student in which course number they are enrolled, their name, their address and course. So suppose Jones is moving from Edinburgh to some other location, right? So if you want to update that, you have to update all the rows of this, which is bad because I cannot just find out one row and update it. I have to find all rows and update it. That's a bad design, right? Delete. So think about this. If I delete like Richard, right? Okay, if I delete about, let's think about deleting the student Richard. So Richard got unenrolled from the course. So in that case, what will happen is these two rows will get deleted. Now suddenly you'd have no information that 9322 corresponds to maths because this row is not there. No other row has maths. So this course number was corresponding to maths. This information is lost altogether, which is an anomaly in itself in the design. Insert anomaly. This is again another interesting thing, which is if you are inserting a new course, let's suppose I'm creating a new course of computer science, but then no students is yet enrolled into it. How do I create a new course number and the course name? Because without a student, I cannot make a row, no? So that's also another problem in database. So if you randomly design databases, it's going to be bad. So that's why we have different concept of normalization that helps us divide like larger tables into smaller ones such that they have proper relationships and stuff. Okay. So it relates a little bit on the functional dependency things, that what is dependent on what. Like for an example, I think it's best taken from examples, right? That if you know the car model of a certain car, then you know that what all different colors it is available in, or which years it has been manufactured in, right? So these are properties of the car model of a certain car, let's suppose. So these things depend on the car model. So you have to handle things in that particular way. So these functional dependencies is what we're trying to like kind of control using normalization. So there are multiple normal forms, right? Data can be represented in multiple normal forms. For an example, in first normal form, we try to make sure that every like data is like has a single value. For an example, Janet Jones has both. They are the same person, so they have the same physical address, same salutation, but they have rented 2 movies. So I could have kept them in the same row itself, but that's not the best design. In first normal form, we try to say that every person, every like column will have a single value in a single row itself. So that is there. That is the first normal form. And generally, the second normal form is what we want to get into. Is basically we want to build primary key relationships in terms of the data that is present. For an example, the name is a separate thing, like names, membership ID is something that you introduce, and the names are different thing, names, physical address, salutation, and which movies they have rented, you have it in a separate table, right? So you want to introduce these single column primary keys that are not functionally dependent on anything else. You want to introduce these columns, member IDs, so that problems like the anomalies that we were talking about doesn't happen. Because if we normalize, say, this table that we saw earlier, it will break down into 3 things. A student number, which contains student information like Jones, Smith, Richard, and the course numbers, and then which student is enrolled in which course. This is a separate table, right? You can say it's an enrollment table or things like that. Now, this solves everything for you. This is just in second normal form, but this already solves so many problems. Like update anomaly, like if you want to update the location of Jones, you just update here. You don't need to do it on all rows. If you want to delete a certain thing, like if you want to delete the student 30 Richard, now you don't lose the information of maths. Now you can insert a new like subject without even introducing a student in that. So all these problems got solved if you normalize the tables properly. So that's the basic funda of how to normalize and stuff. But I think it's more intuitive to me that obviously different objects should be kept in different tables, and that's what is second normal form. And first normal form is keep everything together. that's what is generally expected to be answered. Okay, so that's about normalizations and normal forms. You can read more about them, of course, but we want to be short, crisp, and cover everything that is required. What is SQL? SQL is basically the language. I think you have seen SQL queries. Select the data that you want to get, the columns that you want to fetch from a particular table name, right? Where region ID is equal to 1, where certain conditions are hold true, and then you might also ask the database to give it in a certain order, right? So these kind of syntaxes are created. The syntax is called SQL, structured query language, which will give the result pulled out from the database that you have stored. And you can play this small game. This is a fairly good game, which will give you like clarity on what SQL and stuff does. Okay. But we'll not cover SQL in this session because it will take a lot of time. Okay. So these are mostly the questions. One more topic that I didn't cover much is about transactions, because I want to keep this video short, 30 minutes or so. In transactions, you have concepts around acid basis. Number 1, this is very important question. Read about it. Recovery, states of transactions, right? Dirty reads, writes, the problems of transaction that happens. But it's more of something that you also read in operating systems. You also have the same critical section problem in other places. So read about it a little more about transactions if you have time. But again, in 30 minutes, I think this is a good enough summary of all questions that might be asked in interviews. Now, I think further links that you might need, I've added it over here. The DB book slides are fairly good. If you want to get a full course on database, this is the available course that is there on internet. If you want to practice SQL Hacker Ranks, that is really good. If you're on Algos and it's premium, you can also, there is a course which contains all the lectures for databases and the bunch of questions that you can practice, which are from previous year OAs. So I think that should be enough for this particular video, but I hope this short concise explanation of the database management systems questions helped you. In next video, we'll cover something similar, but I hope this was enjoyable. Make sure that you like and subscribe to the channel. See you in the next video. Bye.